Automating complex data analysis. I'm John McGowan, and I'm the CEO of Mathematical Software. We develop algorithms and tools to automate complex data analysis, reducing costs and increasing results. So the current state of the art in complex data analysis is various tools such as SAS from the SAS Institute, SPSS from IBM, MATLAB from MathWorks, Mathematica from Wolfram Research, and some well-known open source tools, Scientific Python and the R statistical programming language. There are other smaller tools from smaller companies and open source projects as well. All of these tools are programming languages that are specialized for mathematics, statistics, and data analysis. So they have large libraries of mathematical functions, statistical tests, a wide variety of special tools and techniques for data analysis, for mathematics, for statistics, and other kind of specialized functions that you often don't see in standard programming languages like Visual Basic or Java, C++ even. They require a lot of knowledge to program correctly. They all also typically have a special data structure for handling large quantities of numbers, thousands, millions of numbers, or millions of symbols in some cases. These data structures are often called lists or matrices or numerical arrays. So they're highly specialized for these special tasks. There are some differences in the way they are programmed. They're virtually all so-called interpreted scripting languages. They're not compiled like C++, for example. They require a certain amount of expertise to use. They require a lot of expertise in the relevant math and statistics to use successfully. They do require typically a lot of work by a human being to get them to actually produce useful results. The market leader is SAS, which is an acronym for Statistical Analysis System. It shouldn't be confused with SAS, SaaS, which is Software as a Service. SAS is heavily used in healthcare, pharmaceuticals, clinical trials for the FDA, has many other areas where it's highly successful, retail, sales, manufacturing quality control. There's a lot of areas it's very successful. It has sales over $3 billion last year. It is remarkably not that well known in the Silicon Valley for outside of biotech and a couple other specialized areas. It's more popular on the East Coast. It's from a North Carolina company. It's more popular in traditional. It's a very old program. It dates back to the IBM mainframe days, so it's very popular in things like banks and more traditional businesses. And it is the market leader. It's a very full-featured product with a lot of, almost any advanced statistics and methods are available in SAS. It actually has some pretty advanced graphical user interfaces, an add-on tool called SAS Jump. Nonetheless, it's not that well known. Its major competitors are SPSS from IBM. The sales of SPSS are a little unclear. IBM doesn't break them out. They're probably in the range of $300 million to $1 billion. MATLAB from MathWorks has reported sales of $850 million. It's very big in signal processing, more engineering applications, not so much marketing or sales, for example, or medical applications. Mathematica is very specialized. It has sales maybe 40 to 70 million. It's a private company. It doesn't say exactly what its sales are. It's reported to have around 400 to 700 employees, which suggests its sales are 40 to maybe $70 million. Much more money is actually spent on the salaries and overhead for the scientists, engineers, and analysts that use these tools. So these are job postings requiring SAS or these other tools from LinkedIn from May of 2017. SAS is, again, the big leader, has over 12,000 job postings. This is for the entire United States. SPSS is a little over 2,000. They've actually declined. They used to come in third on a lot of job boards, second on a lot of job boards. So SAS would be the big one, SPSS, and then MATLAB. But here we can see that MATLAB has about 7,000 job listings nationwide, according to LinkedIn. Again, there's biases in where these jobs get posted, so don't take these numbers as the word of God or something like that. Mathematica is very specialized in who uses it. It's used by some Wall Street traders or modelers and other specialized areas, academia. NumPy is kind of a stand-in for trying to find out how many people actually use Scientific Python, and it's actually difficult because of it's a free free tools, so there's no real sales, no cumulative sales. It's hard to get a meaningful estimate of how much use there really is of scientific Python and the R statistical programming language. They're both very popular in academia now. They're both popular with startup companies, especially in fields like data science or machine learning. But they're not actually that big relative to tools like SAS, for example, and MATLAB. But being free, they may displace those tools depending on what SAS Institute, MathWorks, and other companies choose to do with their tools. So the bottom line is that the salaries and overhead for the scientists, engineers, and analysts that use these tools, that write these programs and do these analyses, which is actually a very labor-intensive process despite what these tools can do, is probably in the range of $100 to $200 billion each year. So it's much more money is actually spent on the analysts, the scientists, and then engineers who operate the tools, who analyze the data, than the tools themselves. And the reason for that is that actually a lot of tasks that are done in these analyses are not automated. They're not done by computer programs. They're still done by human beings using human judgment and human knowledge. There's exploding use of data analysis. There are a lot of different words for it: data science, analytics, statistics, mathematical modeling. There's a whole bunch of different phrases from different fields. It's nothing new. In fact, it dates back to ancient astronomy, but these programs date typically from the 70s and 80s. These tools like SAS, SPSS, Mathematica, and MATLAB, for example. These are all tools that were largely developed in the 70s and 80s. They haven't changed that much, although they have more comprehensive libraries of mathematical functions, and they added graphical user interfaces in the 1980s. So SAS was originally punch cards for IBM mainframes and similar machines, and it now has actually quite sophisticated graphical user interface in the form of SAS Jump. So it hasn't stayed in the past, but they haven't changed that much since the late 80s when they became graphical user interfaces and interactive development environments and so on. The basic concepts are the same. But what has changed is there's a lot more data today the last few years. We have all sorts of cheap sensors on iPhones and Android phones, specialized tracking watches, Fitbits. I'm showing here something called a Luma Run, which is specifically for runners to help them improve their running. Social media websites, other websites are collecting enormous amounts of data. Disk drives have gotten much larger. Networks have enormous bandwidth, so you have tens of megabits download speeds to your cell phone over wireless networks. Many wireless networks are now in the hundreds of megabits per second, at least within buildings and local areas. And we're pushing to gigabit. There's technology for gigabit wireless networks now. So there's just an enormous amount of data that can be collected, it can be stored cheaply, and there's more and more analysis, therefore, of that data, and it's impacting our society in a wide variety of ways. There's a lot of controversy over Facebook's algorithms for handling news articles, a lot of controversy over things like Zillow that make estimates for for home prices, all sorts of stuff. So the actual use is exploding far beyond the traditional use more in advanced scientific and engineering fields, nuclear weapons research, the space program. All of these areas had these kind of tools 40, 50 years ago, but now people are trying to apply them to all sorts of everyday activities. So the state of the art with these tools remains slow, expensive, it's error prone. There's typically a custom program, a custom analysis developed for each project. It's often very unconvincing. So it's very involved. There are usually hundreds, if not thousands, even tens of thousands of lines of detailed code, selections of statistical tests, a lot of choices that are made by the human being in the process of the analysis, which make the analyses very custom, very hard to reproduce, very hard to understand what they're actually doing. So not only are they error prone and they're sometimes just wrong, but they're often unconvincing to third parties, especially non-specialists, because it just takes so much effort and expertise to reproduce the analyses. You can't easily take one of these analyses in most cases and verify quickly in a cost-effective way that, oh yeah, they've done the right thing. So the total cost of these analyses is very high very often. So typically these scientists, engineers, and analysts are paid anywhere from $40 an hour to several $100s an hour for very high-end analyses, things like Wall Street trading, for example. So let's consider $50 an hour salary and overhead. That's a pretty reasonable number in the United States for a skilled analyst to be paid, and that includes overhead, so that includes things like their computer, their office rent, etc. A 2-week project is 80 hours, is $4,000. 2-month project is 8 weeks, 320 hours, $16,000. A 6-month project, and there are many such projects, is $48,000 in total cost. So the costs actually are of the analyses often greatly exceed the tools themselves. So the tools, Mathematica and MATLAB, are about $2,500. SAS is probably the most expensive, although they're very secretive about their licensing agreements. So you will often hear that a single user license of SAS is around $10,000. It's one of the most expensive. And yet, the cost of the analysis, the analysts, their salaries and overhead, generally far exceeds the cost of the tools. And that is, again, because it's actually a very labor-intensive process, despite all this computerization and automation of some statistical calculations, mathematical model fitting, least squares fits, for example, regression analysis. A number of things have been automated, but the fact remains that probably at this point 80 to 90% of the time is spent in the human being figuring out what to do. So what are the big bottlenecks? These are the two big ones that we've identified here at Mathematical Software. So one of them doesn't occur in every analysis, but in the kind of higher end analyses we're looking at is the selection of a mathematical model. So given some data, typically you want to find a mathematical formula. It can be something very simple like a line, y equal ax plus b, or it can be something very, very complex, and many of the things we don't understand, ranging from quantum mechanics to the blood coagulation system or the processes behind cancer, many of those are probably fairly complex in terms of the mathematics. The point is the person has to look at the data, it can be very complex multidimensional data, and figure out what is the mathematical model. And it's basically human pattern recognition and judgment. You look at graphs, you look at pictures, you look at numbers, and you say, well, that looks a lot like, for example, a bell curve, the normal curve, the distribution that's often used in high school and college grading, for example. So let's say you have a one-dimensional distribution and it has some sort of a peak in it. And the obvious example is scores on tests are typically distributed in a single peak that looks a lot like the Gaussian or the bell curve, the normal distribution. But there are many other possible functions. So in these illustrations here, we see quite a number of competing ones. We see the beta function, we see the Gaussian, we see we see the Cauchy distribution. So the human being has to look at it and recognize it. For simple one-dimensional distributions that we know about, that's not that hard for humans to do, and it's actually quite possible to automate that today with modern pattern recognition. The real difficulty is when these data become more complicated. They're not a simple peak. They're some complicated thing with a bunch of peaks, waves, strange structures. For example, speech recognition is actually a one-dimensional distribution of sound pressure levels, but it's very difficult to figure out what's going on and understand it at a mathematical level. And of course, there are multidimensional data sets. Things like the quantum mechanics or blood coagulation system that I mentioned would be at least several dimensions of data, if not, in fact, hundreds. One explanation for quantum mechanics is that there are higher dimensions that we can't directly observe. So in addition to space and time, there's some sort of hyperspace, and that's the reason for quantum mechanics. And if we understood that, maybe we could achieve faster than light travel, communication, new power sources. That's very far out, but that's just to illustrate the more technically challenging and potentially more valuable problems that an automated system, which can actually operate in higher dimensions that humans can't visualize, that can handle very complicated mathematics that humans have trouble with, even experts, even people who've studied math for many, many years. So that's one of the main obstacles. And the other one is what I refer to as key information on numbers. And the buzzword here is metadata, but that's very cryptic. What do we mean by key information on numbers? Well, when someone gives you some data to analyze, you have numbers. And the numbers, 2.3, whatever. But what do they mean? What do they refer to? That information is often partially in the header or column names in a data table. So this is a simple example where one column, it's actually pretty clear. The first column is date, it's time. It is, in fact, the date, the year 1948, January 1st, etc. Problem is, a lot of times these names are not very explanatory, or they don't include enough information to figure out what's going on. And the second column is an example of this. What is unrate? Well, unrate is actually an unobvious abbreviation for unemployment rate. This is unemployment data from the St. Louis Federal Reserve, but unemployment rate is a remarkably complicated number. There are actually 6 different official unemployment rates, U1 through U6. The one you usually hear is what's called U3. There are different ways to define unemployment, and it actually gets worse. Some people question how the government collects the data for the unemployment figures, how they compute them, the way they're computed has changed over the decades. Some people allege that there's political goals. Generally, unemployment is kind of the report card for the government. The lower it is, the better they look. So it's a very controversial number. So to do a really good economic analysis where unemployment is part of that analysis, you really need to understand exactly what's going on with this unemployment rate that seems like just a number in this table. And this applies to many things. In physics or engineering, you want to know what's being measured. You want to know what the instrument was that measured it, any special issues or problems with that instrument or measurement technique. There can be all sorts of subtleties, and they become very important in some analyses and in getting good results. So this is typically done by human beings. They read through a lot of documents, they look at the fine print that comes with this data table and find out what the definition of unrate is, and they have to do a lot of basically reading of documents, talking to people in some cases. So this takes up a lot of time. It's not something that's currently automated by tools like SAS or MATLAB or Python or R, for example. But if we could automate it, we could greatly speed up the process and make it more reliable because the program can look through all the data, make sure it's collected it correctly, kept a record of all the references, footnotes, etc. that it's using. It's very easy for humans to forget where they found some piece of information and then it turns out they were wrong or their memory failed or they forgot to document it and it becomes unconvincing. So these are the two big technical obstacles, the mathematical model selection, which is currently very human intensive, and it's not just collecting the key information, it's understanding what it means, understanding what the measurements really mean, and that has really profound impacts in some analyses. What statistical tests you should do, what analysis you perform depends on what the numbers mean. So we are developing tools to automate that, to speed it up, to make it more reliable, and greatly reduce, therefore, the cost, and hopefully greatly improve the results so we can actually tackle problems like the blood coagulation system or like the possible underlying phenomenon behind quantum mechanics, things which may have very profound benefits. The blood coagulation system is responsible for heart attacks and strokes, which are actually the leading cause of death is still heart attacks. And so if we can understand the blood coagulation system in greater detail, mathematically, we may be able to adjust it and fix it and make people live much, much longer. But these are really challenging problems. They're challenging the part of the challenging part of the problem that we're looking at is to apply quantitative mathematics to these biological systems, which are currently not that well understood, are very confusing, and do strange nonlinear things that are hard for us to figure out. So what we're looking for as we develop this product and tools and algorithms is data sets, things like the blood coagulation system, for example, or perhaps subatomic quantum mechanics measurements, which are not understood, and they need to be. So we can really prove out these algorithms which perform these more complex recognition of the mathematics in general, and will tell us what's going on. Hopefully will tell us what's going on. So we'd like to know from potential customers or interested parties what they'd like to see automated and why, if they can share their data with us, and we'll probably have to talk about that and the terms and conditions of that, and what we do if we find a cure, not a cure, but we find actually an explanation for the data, a good mathematical model that's predictive. But we can talk about that. What we're looking for is that kind of information and feedback from potential customers and other interested parties. Our website is mathematical-software.com, and I can be reached at ceo@mathematical-software.com.